required. So that was my motivation of the research. I collected some previous approaches of shape analysis. I mean, very mathematical approaches only. The first one is differential manifolds, Kendall, Bookstein, Euler, Pennect. Eigenstructure on Euclidean space, and eigenstructure on differential manifold. And lastly, the function spaces. The first three approaches use some statistical framework, finding some average on their shape spaces. But the last one, the most attractive to me, doesn't give that concept. They just figure out, define the shapes in a function space. First, I would like to introduce the procrustage analysis by Kendall. Here is a simple geometry. A shape, pink triangular, can be transformed into the blue one at a standard position. With that position, Kendall formulate the shape by using a sample mean x bar, which is actually he used a uniform distribution, and with that one he calculated residuals, and they make the shape space S to N. He also gives the notion of distance on shapes between the distance between the two shapes, tau 1 and tau 2. He used that one. So his shape space is modeled on a unit sphere. So one point on a sphere is representing a shape. And then the distance between the two shapes are actually the geodesic on the sphere. That's very concrete model, very mathematical model. Later, another statistician, Bookstein, introduced shape space. Coincidentally, the two people, Kendall and Bookstein, describe the shape space of triangles, but they give different distance. In case of Kendall, he gave the geodesic on a sphere. However, Bookstein's shape space gives Poincare plane. So they have two different approaches, but they reach the same things. So one is for the, oh, I'm sorry, this is a wrong file. It is a typo, positive curvature. I revised last night, but I made a silly mistake. I'm sorry. Anyway, with their method, their approaches, I give an example of 10 triangles, and these triangles are transformed into a standard position, as I show. And then the average values of each vertices are calculated, and finally the mean shape is generated. That's the previous approach, is generating standard shape. Following that way, the conventional method of the shapes on the left figure is from medical images representing a femoral head of a bone. And it is described as 31 points, meaningful points, so-called landmarks. Actually, it is represented by 61 dimensional. X1, X2, X31, 31 points, and then Y1, Y31. So this is defined on the 62-dimensional vector space. And then by using uniform distribution, a standard shape, so-called a mean shape, is generated. We can see clearly the shape on the population set different from the average set generated by the conventional method. So, for example, the triangular shape can be described the conventional method very well. However, this type of arbitrary shape cannot be modeled by the conventional method. So that is the motivation of my work. So I searched the existing concept of average. Very fundamentally, the uniform distribution is used for generating an average, and little bit generalized, infinitely many population set gives the definition of average value of a function. But I could not find relevant concept of the average of functions. I found old literature in 1948, that is the lecture note of Henri Poincaré Institute. It is written in French, but I was aided by a French mathematician to translate it. And I found an implicit definition of a random variable. He focused on the case of function space and introduced two notions. The first one is, if there is a distribution to define it, then we can calculate its average, of course. But if there is no known distribution of the space, then he suggested the second notion of mean is defined as a minimizer of this quantity. Here is a random variable x, and here is y, general y of the metric space, and we measure the distance. And if there is, this is a numeric value now, and if there is some distribution and there is a way, and then we can find some mean as a minimizer of this quantity. This is a definition of fraction. I'm not sure my French pronunciation is correct. Fraction, is it okay? Okay. Due to the definition of being a minimizer, it has a big problem. In point of view, mathematician's view, existence and uniqueness are not guaranteed. So some situation it doesn't exist. In some situation it exists but not unique. So many researchers try to find out under what conditions the uniqueness or existence guaranteed. But one of those trials are by Kendall's group. They try to find the assumptions, but those assumptions are limited in a very, very strong properties. So the problem is we cannot use it in practical use. His hypothesis, but three hypotheses gives some guarantee. His two notions of mean are coincide when these three assumptions are provided. But we have to notice the first one, MS has a finite value. It means it has the mean of his first notion, but it is very difficult to get. That is a big problem. My idea was applying our Wiener space, and most of you know the definition of Wiener integrals, and then I will skip this page. This is a membership of our Wiener major space. Well-known Wiener integration formula. So I hoped this is a function space integral, but this is a Lebesgue integral. In finite dimensional, it can be calculated by Riemann integral, so we can compute it. So that was my hope, firstly. The theorem from the book by Ye tells us some statistical framework on the Wiener major space. The equation on the way means the Gaussian distribution, normal distribution, and the second one, if we give xt1, xt2 the same t, then we can think this is a variation, x squared minus 0, and then it gives some kind of variance. The variance at point t could be the minimum of t, and t would be the t, so it would be t minus a. So we can see the Wiener measure is actually probability distribution with average 0 and variance t minus a. So this is the key idea of my development. How about our average value? Sorry. Here, at each point, we see 0 is a mean value. So, for each t, the function defined by that could be the average of the population set, the whole set C naught AB. I mean, here we can find 0 function is a population average. So, this population average is discussed in relation with Fresh mean. This is my theorem to clarify the relationships. Using that function on Fy, we can see our population average is actually a Fresh mean, the mean in the sense of pressure. So, I could convince my development is meaningful. So with that concept, I try to generate a sample average now. We have a subset of C naught AB. We have a set of continuous functions, whether it is finite set or infinitely many set. We can find some average using the previous concepts. The problem is how to define it. We expect it is, if there is an average, it should be another function. And we need to assign a value for each point t. But how to evaluate the value at each point t? We have many functions from A to B, from every continuous function on C naught AB has a value 0 at the initial point A, and at a certain point T, it has many different values. But how to choose the average of them? If it is finite, people usually do that 1 over n, uniform distribution. That's the conventional way, but I didn't agree with that. And I think there might be a way. So I try to use the structure of the Wiener space to generate it. So very well-known measurable function, capital Xt, is used because we know that in the previous prepositions, it follows average 0 and the variance t minus a. So I use that one. Demonstration of the function. We have a continuous function. The capital Xt, that measurable function, assigned to the single real variable here, real value here. So I try to employ the system of measurable set Xt and use that function. Actually, it can be regarded as normal distribution, varying Gaussian. But for each point t, the variance is different. The mean value is 0, same. However, the variance is different. The variance is xt follows normal distribution 0, t. I use that. For each t, it has different values. I mean the vertically. The distribution of these values have Gaussian distribution or normal distribution. So it is described in that way. So, and another thing is the average formula for measurable function is found in the book by Rudin, the real analysis. I think it is the third edition, so I use that one for each random variable, capital Xt. So this is my average formula. This is according to Rudin's definition of measurable function, capital X. I use his definition for evaluating the average value at each point t. And this t develops from A. Actually, half-open interval. From A greater than A and to B, I can develop this definition. So in calculations, I need to compute it by computer programming. So I use that Riemann integral to evaluate them. Here. Oh, I'm sorry. Yes, you are correct. Thank you for pointing it out. T minus A, yes. So my figure, yes, my figure shows from 0 to B, so I put them. Yes, thank you very much. Yes. This is an illustration of my average. From alpha beta to beta, so-called cylinder set, it is distributed, the value at the point t is distributed within that interval, and the generation, the equation 7 gives the point where we should assign the average value at that point. Now, we need, that is constructed from the point A greater than A and less than or equal to B, but we need to assign the value at the point A. But we can't use the equation 7 for the point A because A is a singularity, because the denominator of that equation is 0. However, all continuous function within our sample set has the value 0. 0. So we can say the average value of that point could be 0. The population set is just 0. So XA is 0. Now we can define our average shape with this equation for the point t greater than A, and at point A we define it as 0. So our average function is defined. But the problem now, in practical use, there is no need such things, but I would like to clarify my definition would be mathematically concrete. So our average is located within the cylinder set again, and moreover, I hope it would be a continuous function. Then it would be a nice setting. And these are valid. And now with the theoretical, mathematical justification of the two theorems, I now can make formally the definition of average function here. Why I discuss the theorem 4.1 is, in case of ratio mean, it doesn't hold. If we find out something about something in the sense of ratio, the average shape is sometimes deviated from population set. It happens in ratio means. So I want you to check this part. And I also define variance and score. So I actually want you to figure out the statistical framework on the Wiener major space. But the variance was a little bit tougher than the average. The natural way is using Fresch's idea. This is an average just defined in the previous section, and this is arbitrary x within the sample set C, and the distance between the two means the deviation from the average. That's the usual concept of statistics. So that is actually Fresch's functionals. So I want to try this one as a variance of the system. To justify it mathematically, I want to I want to show from this functional, our average defined in the previous section is actually a mean of pressure. So this could be an optimization problem, but usually this type of optimization problem could be proved by Euler-Lagrangian approaches, but I didn't follow that because Euler-Lagrangian approach requires differentiability, but I tried to make my model without a differentiability, but because that is too strong. Another reason is in the Wiener space, the set of differentiable functions has measure 0. So I try to avoid that fact. Instead, I employed Kato variation. Without differentiability, we can get the similar result to Euler-Lagrangian approach. So with that concept, I could see the average in my definition is actually the minimizer of the pressure functional. The corollary shows that one. This is actually, this indicates the Rudin's definition of average of a measurable set. So, our mathematical definition of variance is just shown in the previous theorems. Now the problem is, this is not always calculable. That's a big matter. In case of average, we could calculate it, but this is for arbitrary subset of C node AB. Usually, Wiener measure is based on the finitely based, finitely many integrals, but not all sample set C can be described in that way. So this is a bottleneck of calculations. So I suggest for practical use the secondary one. This one and this one. That can be calculated. So if calculation is possible, we can make it more practical. But that is certainly not exactly the same as mathematical variance. But this is just practical variations. If one can calculate the mathematical variance, we can use that. Next, I give the concept of score. In statistics, the score means the normalized deviation from an average. I try to make it the similar stuff, but different from fundamental statistics. The score here is defined as a L2 norm. So L2 norm has positive value all the time. But in statistics, the score can have a negative value. So I made it quasi-score instead. Using the variance, we can define the quasi-score. This is an X, an element in our sample set. This X bar is our average, just defined in section 2, and variance defined in section 4. Or the practical variance, if the mathematical variance is not calculable, then we can figure out the new numeric variable. X is function. These two elements are functions. These two functions can be characterized by a numeric value, z. So easily we can figure out how far they are. If x is given and this function is far from the average, from the center, that can be easily understood concept. Actually, this is from my model using the Venus space. However, that concept can be used in any metric space. If the metric is defined on the space, then we can measure the deviation in that way, standard deviation. The model is applied to some real shapes. I made synthetic shapes, very different ones. Round shape, square or rectangular, or very different star shape. Here, 7 shapes are modeled, and by a Kendall's Procrustean analysis, they are transformed into a central point, and I generated average defined by the Venus space, and black dotted line shows the average shape. But this may not be, this is too extreme. I tried to just find out how different from the conventional method. I measured the score. According to my implementation, my experiment, the conventional method shows a variety of scores, but the average defined by the Venus measure space shows very small values of scores. So I think I interpreted my average is most representative of the group. It has just 7 elements in the sample. So the sample number is not very big. However, I could see the difference. The conventional method used the average, and the score has these values. But our method shows least variability. So I think my average represents better than the other statistical framework. But some people may not agree with me. Yes. Here is a real applications. In femoral head, which I showed at the beginning of my motivation, the femoral shape using conventional method doesn't show the standard shape of its own. But this femoral head, always they are located within the sample set. I've told the theorem 4.1, the values of xt is always within the interval alpha t and beta t, always located in the cylinder set. This proves that one. Conventional method doesn't generate this type of average all the time, but mine always located in the sample set. So I can say my model formulates an average of function set explicitly, which has not been introduced before my work, in my knowledge. And my model provides a statistical framework of function space, average, variance, and score altogether. This can be used for shape representation on Venus space. And my score gives some measurement for global deformation or shape variability. And this can be a tool of general evaluation for statistical method, because this concept is very important in shape analysis. With the change of shape is used for indication of some abnormality of shapes. And this model enables us to express shape variation with an average shape. It means I didn't put this concept here, but we have any shape can be expressed in terms of mean shape, average shape. This could be basis member of my shape space. This could be some parameter. It means any shape instance can be expressed in terms of the basis and average shape. So we just observe this part, how shape is variable from the average shapes. So that's why we try to generate a standard shape from a shape space. So we can do that. Our shape space is the Wiener measure space. So basis could be, I find that on Hilbert space. Hilbert basis I generated. Of course, to calculate such things, finite dimensional Hilbert basis I generated and then used with some parameter values, and that can be introduced. So shape variability is mathematically and compactly expressed by that way. That was the purpose. And during those processes, I could not find any concept of explicit formulation of average, so I developed that average using the structure of Wiener measure space. That can be expanded to three-dimensional model, and if I success, I can do three-dimensional volumetric measurement, which is in great need in medical image analysis now. That's all. Thank you very much.